Deep inside a fiber optic cable, data travels in perfect, predictable intervals. This single data packet is moving towards a user's screen right now, part of an orderly line of light pulses, operating well within the network's physical limits. Then, human behavior disrupts that order. At a specific geographic moment, millions of individual people press play on the exact same live broadcast. Millions of separate requests rush outward, and the resulting video data floods backward. Our packet arrives at an internet router, a physical junction, just as thousands of other data streams reach that exact same point. The traffic volume instantly exceeds the hardware's maximum bandwidth. People do not coordinate their internet usage. We generate massive, unpredictable demand spikes, crashing directly into physical cables that possess absolute maximum limits. The router catches excess packets in a finite memory buffer, processing them sequentially. Once this buffer reaches full capacity, arriving packets are immediately discarded. This initiates a destructive loop. Sending servers detect missing packets and automatically resend them, bombarding the already full router with duplicate data. The hardware is now working at absolute maximum capacity, burning processing power to handle traffic that it will ultimately be forced to drop again. The volume of useful data successfully crossing the network falls to near zero. This state is known as congestion collapse. To prevent network failure, engineers implement systems designed to maintain 4 strict conditions: keep the data flowing smoothly, allocate bandwidth fairly among all users, maximize the efficiency of the physical cables, and keep the hardware stable under pressure. They achieve this through 2 broad engineering philosophies. The first is open-loop control. This is proactive prevention, establishing hard rules before data is even permitted to enter the cable. Open-loop systems restrict the total amount of data allowed in transit. The network evaluates packets at the perimeter, assigning priority to critical data and outright denying admission to new connections if the network is already nearing capacity. The second philosophy is closed-loop control. This is reactive. Sensors monitor the active flow, and if a router begins to struggle, the network adjusts on the fly, sometimes deliberately sacrificing a small fraction of packets early to signal that a bottleneck is forming. Those early drops, or specially generated warning packets, travel backward through the network, actively telling the origin servers to slow their transmission rates. Yet while these macro policies protect the hardware from total failure, they manage the symptoms rather than the cause. The traffic arriving at the routers remains erratic and clustered. To fix the shape of the traffic itself, networks rely on micro-interventions. Algorithms sit at the edge of the network, capturing chaotic, concentrated bursts of data and actively reshaping them into evenly spaced streams. The most rigid method is the leaky bucket algorithm. Data arrives from the user in unpredictable waves, falling into a holding queue. At the bottom of that queue, a mechanism releases the packets into the network at one absolute, uncompromising rate. This timeline charts exactly how the algorithm functions under pressure. The outgoing transmission line remains perfectly flat, regardless of the chaos inside the bucket. If an incoming burst is larger than the physical capacity of the bucket itself, the excess data overflows and drops. The algorithm's greatest flaw appears when the traffic stops. The release gate continues turning at its exact fixed interval. Because it cannot bank these empty intervals for the future, potential transmission capacity is entirely wasted. The leaky bucket delivers absolute predictability, ensuring downstream routers never face a sudden spike. But it severely limits applications like web browsing, where humans naturally request large amounts of data in short, sudden bursts. To solve that inefficiency, engineers deploy the token bucket algorithm. Instead of wasting quiet periods, this system actively builds a reserve, saving unused capacity for the precise moment the user needs it. In this system, the bucket does not hold data packets. It holds permission tokens. The algorithm generates these tokens at a steady, fixed rate. For a data packet to enter the network, it must first claim and consume a saved token. During idle time, the tokens accumulate. When the user requests a web page and a massive burst of data arrives, the system spends those accumulated tokens all at once. The entire burst is authorized and moves through the gate instantly. This side-by-side graph highlights the mechanical difference. Under a sudden load, the leaky bucket's output remains rigidly flat, forcing packets to queue or drop. The token bucket dynamically accommodates the initial spike by spending its reserves, only flattening out once the token supply exhausts. The token bucket is effectively the leaky bucket paired with a savings account. It maintains the mathematical safety limits required by the hardware, while finally aligning with the erratic reality of human behavior. Back inside our overwhelmed router, our trapped packet approaches the front of the queue. Sitting directly at the exit port is an integrated token bucket shaping module. Because tokens were generated while it waited, the packet claims its permission. It passes through the gate, breaking free from the congested hardware. It is no longer trapped in a chaotic surge. The shaping module has isolated the packet from the burst, placing it into a mathematically controlled, perfectly spaced sequence. By enforcing these rhythms at the source, the network ensures that the next router down the line receives a predictable, manageable stream, neutralizing the threat of congestion collapse entirely. These exact algorithms govern our daily connections. Internet service providers run token buckets continuously in their server halls to enforce the specific download speeds you pay for, giving you quick initial bursts to load an article before capping large file downloads at a steady, fixed rate. Quality of service systems combine both of these methods simultaneously. They use these algorithms to identify real-time data, like live video, guaranteeing it always has a fast-tracked lane through the network, staying fully protected from massive background downloads. Our packet reaches its final destination. It arrives at the living room television in perfect sequence, alongside millions of others, rendering a seamless live image without a single moment of buffering. Every clean video call, every instantly loading web page, and every seamless live stream relies entirely on these invisible mathematical gates, quietly filtering the chaos of human demand into the structural order of the internet.